Alright, so section 9.9 is going to be talking about actual applications for this. So when we're talking about the revenue function, what the derivative gives us, which by the way, what you'll see in your textbook and on the homework and other places is sometimes they will call the marginal revenue instead of R prime, they'll say MR bar. That's because that's a bar on top. Okay. Also, if you're given a cost function, they'll say marginal cost. And for profit, they'll have marginal profit. So if you want to know how much money you're actually making, then what you're going to do is that you're always going to be taking the amount that you made overall minus the amount it cost you to make that product. So what is the derivative? So remember, R of X means that's how much money you're making if you produce X units. So if we look at the derivative, that would be dr over dx, which would be talking about the change in your revenue per item or unit that you're making. So what the marginal revenue tells us is how much the sale of one unit or one item will increase or decrease our revenue. Okay, the same thing occurs when you're talking about the cost. So the marginal cost function tells us how much the production of one more unit will cost to produce. And same thing with profit. So one more unit. So, since you guys are business majors, I'm sure that this isn't a foreign concept to you. The fewer items you produce, the more it costs you to produce those items, right? But the more items that you make, what happens is that you're able to buy things in bulk, you're able to minimize the cost, you're able to increase the revenue because you're pumping more things out. So what happens is that you're going to hit this really nice sweet point where it costs less to make an object, which means that you get to make more money, right? So, first off, suppose that the total revenue function for a commodity is R of X equals 64X minus 0.2X squared. So what we want to do is find R of 100 and what it represents. So, when we do this, it's going to be 64 times 100 minus 0.02 times 100 to the second. So we're going to have 64 times 100 minus 0.02 times 100 squared. And that means that when we make or produce 100 items, we can expect to have a revenue of 6,200. Now, to find the marginal revenue function, what that is going to do is that is going to be R prime of X, which remember we can rewrite as MR bar. So we take the derivative, so that's going to be 64 minus 0.04X. So now we want to find the marginal revenue at X equals 100, and we want to tell what it predicts about the sale of the next units and the next 3 units. So, R prime of X, R prime of 100 equals, so it's going to be 64 minus 0.04 times 100, which is going to give us 64 minus 0.04 times 100. That's going to give us 60. What that means is it's going to cost, or not cost, we will make $60 on the 101th item produced. And if that trend continues for the next 3 units, we can expect to make 3 times that, so that means $180. Now, what we want to do is want to see how good is that actually. So, what we want to do is want to say, hey, did I actually make $60 on that 101 item? So, we're going to take the revenue we made from the 100th item and the revenue we made from the 101th item and subtract them and see if that matches. So we're going to take R of 101 minus R of 100. R of 101 is 625 or 6259.98. And R of 100, well, we found that up there, that's 6200. And when we subtract the two, we get $59.98. So what that means is that the derivative gave us a very good estimate of about how much money we can expect to make when we produce one more unit. Now, suppose that the demand for a local cable company service is given by P equals 120 minus 0.4x, where P is the monthly price per prescriber in dollars, and X is the number of subscribers in hundreds. So, what we want to do is find the total revenue as a function of the number of subscribers. Okay. So, remember, if demand is this, then the total revenue is going to be the demand times how many we have. So that's going to be 120x minus 0.4x squared. Great. Now we will find the number of subscribers when the company charges $80 per month for cable service. So remember, P is the monthly price per subscription, and X is the number of subscribers. So we're going to have 80 equals 120 minus 0.4x. So we want to solve for X because that's the number of subscribers. So when we solve for X, remember, we're going to subtract 120 from both sides. So we're going to have 80 minus 120. And then we need to divide both sides by negative 0.4. And we're going to get that we're going to have 100 subscribers. Now if we want to find the total revenue, which we found up here, revenue, we're going to have that revenue at 100 subscribers is going to be 120 times 100 minus 0.4 times 100 squared. So our total revenue when we have 100 subscribers is going to be $8,000. Great, now we want to find and interpret the marginal revenue when the price is $80 per month. So we're going to find R prime of X, which is going to be 120 minus 0.8x, and we want to find and interpret the marginal revenue when the price is $100 per month. So it might feel like we need to plug 80 into this, or $80 per month. But remember, when the price is $80 per month, X equals 100. So we actually need to plug 100 subscribers into this. So when we plug 100 into this, let's see what we get out. So we get out 40. Now let's do an interpretation of this. Revenue's in dollars, and this is per subscriber. So what this means is that if we added one more subscriber, we would be making $40 more per subscriber. Great. All right, now for 3, suppose that the total revenue for a certain product is given by R of X equals 25x minus 0.05x squared. So what we want to do is that we want to use the graph below to determine the number of units that must be sold to maximize our total revenue. What is the maximum revenue? So when we look at this, if we want to maximize a revenue, we want a revenue to be the highest it can possibly be. So if we look at this graph, it hits its highest point right here. Okay? Now, if we think of this and do like a little interpretation of what this means, if we look at this side and we draw the tangent line, notice that our tangent line is positive, which means that our marginal revenue is increasing. However, the second we go beyond this point here, our tangent line is going to be negative, or have a negative slope, which means it's going to be decreasing. So if we look at this graph and we kind of guesstimate where this happens, it looks like we're going to see a maximum revenue when we have 250 units. And it also appears like a revenue is going to max out at roughly about 3,000. Okay. Now, if we look at the graph of r prime below, and we use this to find the maximum and when it will occur, okay, well, we're going to have a positive r prime value, because remember, the y-axis is our r prime. We're going to have a positive r prime value between 0 until we hit 250. After that, what we can see is that we're going to dip below the x-axis, which means that our revenue value, or r prime value, is going to be negative. So what we see is that when we look at this point, we're still going to have that the number of units we sell to maximize is still going to be 250. So the same thing that we got above, 250. Also, if you look here, well, what's r prime? R prime is 0, and the cool thing is if we look at the graph above, well, this is a tangent line. What's the slope of a horizontal tangent line? It is also 0. So we can find maxes and mins by finding when the derivative is 0. Whoops. All right. Next one, we're going to be looking at cost functions. We want to find the marginal cost at 8 units and tell us what this predicts about the cost of producing one additional unit. So C prime of x is going to be, well, the derivative of 300 is 0, the derivative of 6x is 6, plus 0.1x. Now, to find the marginal cost at 8 units, we're going to plug 8 into this. So C prime of 8 is going to be 6 plus 0.01 times 8, which is going to give us, whoops, $6.80. So what that tells us is that we predict it's going to cost us $6.80 to produce one more item. Okay, that means it's going to cost us $6.80 to produce the 9th item. So let's check this out and see if it's true. So let's do C of 9. So we're going to plug 9 into the original function up here, minus C of 8. So let's see. C of 9 is going to equal 358.05. And C of 8 is going to equal 351.2. So when we subtract those two from each other, what we get is we get $6.85. So remember, this is an estimate and this is the actual. So really quick, I just want to point out why this isn't exactly the same as this. So what we're doing is that our cost function looks like an upside down parabola, like so, okay? Or it could look like a regular parabola. Either way, what we're doing is that we're looking at a certain spot and we're using a tangent line, so a straight line, to try to make a prediction. Now when we do that, see how there's all that space in between them right here? Well, what we might predict is something here, but the actual is something here. So in our case, we tried to predict, hey, what's going to happen at the 9th value? And this is what actually happened. So we got a prediction of $6.80, when actually it's going to cost us $6.85. So remember, this is just a prediction of how much it's going to cost. All right. Next, we're going to be looking at this graph. So given the graph of the cost function, C of x below, determine which will cost more, the 101st item or the 501st item. Okay, when does manufacturing become more and less efficient? So if we look at this, we have 100 right here, and we have 500 right here. And what we're really interested in looking at is we're interested in looking at the tangent line. So if I draw a tangent line here for the 100th item, and I draw a tangent line here, which tangent line is steeper, aka greater? Okay, so what I can see here is that I have a bigger tangent line than I have here. So what that means is that it will cost more to make the 101st item because I have a steeper tangent line, which means that it's going to cost me more money to produce the 101th item than it would to produce the 500th item. Than the 501st. So when does manufacturing become more and less efficient? So what happens is that our cost of manufacturing is going to be more efficient the more units we make. Because as we go along, our tangent line is getting more and more horizontal, which means it's costing us less and less and less to make items. What we don't want to happen is that we don't want to have a negative slope, because that means it's actually costing us money to make more items. Okay. Now, using the graph below for the sale of 100 items, 400 items, and 700 items, we want to rank them from the smallest to the largest amount of profit received. Okay. We also want to explain our choice and note whether any of these scenarios result in a loss. So, here's the deal. I always like to color these. Is that we have our revenue, and then we have our cost function. Okay. So, a key thing to remember is that your profit, profit is your revenue minus your cost function. So, in order for you to have a positive profit, what you want is that you want your revenue to be greater than the cost of the items. So if we look at this first, like the tail of this fish, it kind of looks like a fish here, bloop, with its little gills. Anyway, if you look at the tail of the fish, what happens is that it costs more than we're making to produce this item. So what I can say is that when x is less than 150, so when we're looking at this little tail here, what's going to happen is that our cost is going to be more than our revenue. Now that's not good, because what that means is that means that our profit, okay, is going to be less than 0. That means that we're going to have a negative profit. Now, if I look above this, what I see is that when x is greater than 150, I see that my revenue is going to be greater than my cost, which means that my profit is going to be greater than 0. Okay, so when I'm looking here and it says rank them between 100 items, 400, and 700, well, if I look at 100, I'm going to end up having a negative revenue. When I look at 400, I have a nice big difference between my revenue and my cost. And if I look at 700, I have a small difference between my revenue and cost. Right? So if I had to rank these, I would rank them from the largest, or from the smallest to the largest. I would go 100, 700, and then 400 would actually give me the biggest profit, because I would get the biggest positive difference between R and my cost. All right, very last example here. A firm in a competitive market must sell its products for $150 per unit. The cost per unit per day is 70 plus X, where X represents the number of units sold per day. Find the marginal profit function. So, what we have here is we have the revenue. So remember, revenue is the cost of the product times how many you sell. And then the cost per unit is 70 plus X. So you multiply that by X, and that's how you get the total cost function, right? Because it's the cost per unit times how many units you make. So to find the profit or the maximum profit, we have to find the derivative first. So that's going to be 150 minus 70 plus 2x, which if we simplify this out, that's going to be 150 minus 70, so that's going to give us 80, minus, remember you have to distribute that negative, minus 2x, so that'll be p prime of x. Okay, great. Now, if we actually graph this function, what it would look like is it would look like a downward parabola. So if we want to find when it's a maximum, we have to find this peak here. So finding that peak there, notice that the tangent line is going to have a slope of 0. So what we need to do is set this guy equal to 0. So we're going to have 0 equals 80 minus 2x. And then when we solve for x, we get that x is 40. So the maximum profit the company will see in one day is going to occur when x equals 40. That means when they sell 40 units. Any less than 40 units, they're not going to be making as much money per unit anymore, and they're actually going to see that they start to lose money. Okay, so that is it for these solutions. Okay, just keep in mind that we are doing applications, so thinking of it in a real-world context is a great idea.